Hello to all. Welcome back to my another video on silicon nanowire junctionless FET 3D and 2D structure simulation. So in this video we will discuss about the silicon nanowire junctionless FET and how we can create a junctionless transistor. So we will cover junctionless FET. We will learn about that what is junctionless FET, what are the various challenges in junctionless FET, how we can simulate this device, and the last one is nanowire structure, that is basically a junctionless FET. So we can create the junctionless nanowire structure also, and it is simulative also. We will see the simulation also in this video. So let's get started with the video. So we all know that the transistor has been derived from vacuum tube transistor to the latest transistor, that is, you can say FinFET transistors. FinFET is basically used in all the technologies nowadays present. Now, apart from the FinFET, we derived from planar double gate transistor. There is another transistor that is ultra thin SOI transistor, that is basically silicon on insulator transistor. It is a different technology. Then again, gate all around nanowire FETs, gate all around cylindrical structures, gate all around MOSFETs are also there. So these are the various transistors that have been evolved from the classical transistors. Now I would like to introduce what is junctionless transistor and why we have moved from junction transistor to junctionless transistor. In junction transistors, the basic reason is that the short channel effects are very high. Second, the fabrication of junctionless transistor at very small scale is very difficult and very costly. So, Tyndall Institute of Ireland introduced or fabricated the FET which has no source and drain junctions. The device have become a promising candidate for the further research. A junctionless FETs consist of heavily doped ultra-thin silicon film which has the doping concentration of 10 raised to power 19 centimeter per cube with the gate work function of 4.6, which modulate the carrier concentration present in the silicon nanowire. Junctionless FET do not have the metallurgical junctions because silicon thin film is uniformly doped. Uniformly doped means all the concentration in all the silicon thin film is equal. Now doping is high, we have to create a channel, so we have to keep the work function high, so it will deplete the channel when it is in the off state. So basically junctionless transistor is an on resistor. So it will be off when the work function of the gate is higher. In comparison to the junction based transistor, the junctionless FETs operates on the different current mechanism. Basically in junction FETs, the current flows on the surface of the transistor of the channel, and in the junctionless transistor there is a bulk conduction we call. Bulk conduction means the current flows between the source and the drain in the middle of the silicon film, thick film. So it is basically a bulk conduction. Now we can see that junctionless transistor has 4 modes, or you can say operates in 4 modes, that is fully depleted region, partially depleted region, flat band mode and accumulation mode. So fully depleted means when your gate voltage is less than your 0, that is your fully depleted region. Partially depleted region, when your gate voltage is greater than threshold voltage. Now, flat band means when your gate voltage is equal to flat band voltage, mean your channel just started the current conduction, and in accumulation your gate voltage is greater than flat band voltage. So this is the basic of junctionless transistor, how it conducts. Now we will see the performance parameters in the junctionless FETs. First is mobility. Now it has bulk conduction. So the impact of mobility in the junctionless FETs is degraded, means mobility degraded in the junctionless FETs. So we have to keep in mind while designing the junctionless FETs, we have to keep the track of mobility. Carrier ballisticity. Carrier ballisticity is basically that embedded flow of electrons or holes from source to drain region. So carrier ballisticity in junctionless FET is higher. Next is temperature dependence. Now again here we will consider that when the junctionless FETs are performing in the higher temperatures, the mobility will degraded, because mobility basically comprises of surface scattering mobility, phonon mobility, and robustness mobility. Okay, so all these mobilities are basically temperature dependent, and if the temperature rises, mobility is again degraded to some extent. Bias temperature instability. Bias in temperature instability is related to basically the degradation of gate oxide. So it is very less in the junctionless FET, because junctionless FETs are not that much sensitive to the bias temperature instability, or you can say gate oxide degradation, due to the fact that bulk conduction of the current. Now, low frequency noise. Basically, this parameter is equals to, or you can say this parameter is very related to the signal to noise ratio. So junctionless FETs are having comparable, or you can say very high signal to noise ratio as compared to MOSFETs. Now short channel effects. Now short channel effects are basically the effects when we are scaling down the channel length, we face some kind of difficulties in terms of drain induced barrier lowering, in terms of threshold voltage roll off, in terms of gate induced drain leakage, in terms of leakage currents. So all these are the performance parameters that we have to keep in mind while designing the junctionless FETs. So next is, I would like to discuss about the challenges in the nanowire FETs. First challenge is random dopant fluctuation. Now, it is a junctionless FET. All the particles are randomly placed. So, there is a high chance of random dopant fluctuation. High source drain series resistance, sensitivity to process variation, and the most important is band-to-band tunneling in the off state. Now, band-to-band tunneling in the off states are basically due to the presence or making of BJTs, bipolar junction action, in the junctionless FET due to the overlapping of conduction band of channel to the valence band of the drain. So we have to keep in mind that when designing the junctionless FET, all these challenges will come, and we have to design the structures in such a way that we will overcome these challenges. Now, in the literature, various architectures have been proposed. First of all, junctionless accumulation mode field effect transistor, efficient volume depletion using junctionless field effect transistor, bulk planar junctionless FETs, and non-uniform doping in the junctionless FETs. So we are not going to elaborate this, but these are the different structures that will remove the problem of junctionless FETs. Apart from this, we will discuss now that how we can easily simulate the any structure, not the structure in the atlas, we can simulate the any kind of structure. It is a device, basically atlas is the simulator of Silvaco Tcad, and it is a device that has the framework. It numerically evaluates the behavior of semiconductor device alone or with the several other physical parameters. It evaluates the device characteristics by solving the device physics equation that explain the charge distribution and conduction mechanism. It also provides a diverse set of physical models like Fermi direct statistics, advanced mobility models like Phillips models, like Lombardi models. So all these models of your mobility has been present in this Atlas simulator. It has fully integrated capabilities and it has very interactive runtime environment that is deck built. It has graphics and analysis environment that is Tony Plot, and it has simulator known as Anthena and Supreme. It uses very powerful and sophisticated numerical techniques during the solving and making initial strategies. So I would like to share with you this very brief introduction of Atlas simulator because we are going to design the silicon nanowire junctionless FET using the Atlas simulator. So basically, when you have to design, you have to specify these three parameters, or you can say these three steps, that is physical structure. First, you have to design the physical structure, then the model to be used, then the bias condition of the device. So I would like to introduce that Atlas, Davided, Anthena, and deck built are the integrated part of the Silvaco Tcad. So Atlas is the device simulator, okay? And they've added structure mesh edit is it has you can create the structure, you can mesh that structure, and also you can process simulation that structure. Now that you have created a structure file that goes to device simulator and it will provide the runtime output with the solution files. So this is how your Atlas device simulation will work. Now Atlas programming, we have to do the programming in the Atlas. So first of all, we have to write the with the command go Atlas, and then we will define whether you want for the 2D mesh or 3D mesh multiple structure. Now after that, structure needs to be properly defined. Structure specification including meshing, region, electrode, doping of the device. Mesh basically is the smallest entity where the evolution of device equation occurs at every node. Now we have to understand if you have given the dense meshing causes this results in the higher number of nodes and greater accuracy, but lightly meshing is faster but less accuracy. So you have to plan accordingly and intelligently for the meshing and to optimize run and accuracy. Next section is material section where you have to define material, models, contact, interface definitions also. The numerical models that are used in solving the equations are needed to be specified. The solution are to be specified. Specifically, the statement used for the solution specifications are log, solve, load, and save. Finally, you can easily extract the structure in the Tony plot in the 3D or 2D schematics. Now, let's see what is cylindrical nanowire junctionless FET. In the figure, you can see it is a cylindrical structure and it has a gate, it has an oxide as well. Inside the gate, oxide as well. So nanowires suggest as gate all around nanowire FETs. The gate electrode wraps around the entire silicon channel. The gate all around architecture basically facilitates an efficient gate control of the channel charge and reduce the influence of drain region on the electrostatics of the channel region. As a result, a short channel effects such as DIBL, threshold voltage roll-off, and so on are significantly suppressed in the nanowire junctionless FET. Nanowire FETs exhibits a close to the 60 millivolt decade subthreshold swing due to the enhanced gate control. Now let's see how we can simulate the nanowire junctionless FET. So first of all, when you are designing for the junctionless FET, you don't need to worry about the source and the drain doping. So you can give just one doping to the channel, or you can say to the silicon thick film. So here I have a different approach in which I have already set, or I have already defined the variables for the each and every step. So first of all, I have defined the variable for channel length, then radius, then oxide thickness, source doping, drain doping, channel doping in case of junctionless FET, gate metal work function, permittivity, and the last one is the source and the drain extension. Now, after that, you need to specify the structural specification or the mesh. Now you can see we have defined the mesh structure by 3D cylindrical. Now it has, in the cylindrical or 3D mesh structure, you have three components, that is radial meshing, angular meshing, and Z meshing, Z axis meshing basically. So we have the variable R which is corresponding to the radius, and we will add or subtract in the case of silicon nanowire. So in angular mesh, we have location of 0 to 360 degree. So whatever you are going to give on the radial mesh, it will directly expand it to the angular meshing as well. In the x-axis, or you can say z-axis meshing, you have to specify the region, extension of source, extension of drain, then extension, or you can say the presence of channel. So this is how you can easily create the structure. You can also see the structure after simulating the code. Now we have to define the region. Now I would like to love if my all the regions are perfectly designed and specified. So source region, we have to give the material to the silicon to the source region. Similarly to the channel region, because it is a one silicon thick film, so you can provide the same material at the different, you can see that the radius is also same, but angular mesh is also the same, but the z-axis mesh is different for the all the three region, for the source region, drain region, and channel region. Now we have to specify the oxide as well. In the oxide, we have to place the oxide on the silicon nanowire. So under the gate, so we have to provide the parameters, or you can say the dimensions of that particular area. So we have kept the material as HFO2, hafnium oxide, which is having a very good on current. After that, we will specify spacer material and spacer regions. So similarly, we have to specify spacer material and spacer region as well. Now electrode definition. Now I have designed that source, drain and gate are my electrodes. So these electrodes should be placed where they are necessary most, that is on the source side, that is on the gate side, and that is on the drain side. So material here we have used aluminium. You can use polysilicon and other metals also. But due to we need to decrease the series source and drain resistance, we have to keep the track or optimized material we have to use here. So after that, doping needs to be done. You can see it is a one single material is there. So you can, I have shown that how to write Gaussian and uniform both, and you can see Gaussian is the similar to the uniform as well. So we don't have to worry about that. The doping region is source and the current is 10 raised to power 9. No, the doping region is your drain, source and channel. Now we have to specify various models that has been already present in the Silvaco Tcad, that is basically Fermi Direct, SRH, Auger, CVT, FNOD, BTBT dot non-local, because this device is a very small device, so we have to consider this. CCS mobility model, FLD mobility model, Con mobility model, band gap narrowing, BT, KL Boltzmann model, temperature. Okay, and after that we have defined the methods, Newton-Raphson method, and that is with the limitation of 5. Now we have output band structure. On the output side, other electron holes, potential, all the things have been specified. Next is contact definition. We have to provide the contact definitions to each and every electrode, that is source, drain and gate. On the gate electrode, we will provide the gate work function that we have used here. Gate work function of 4.9. Okay, so next is your solve section. In the solve section, we will ramp the drain and provide this stable input to the gate signal, gate device, gate. So here we can see that this is how you can calculate all the electrical parameters of the nanowire junctionless FET. Now to visualize the result, we have to save the results in the Tony plot, and we will use the result in like silicon nanowire.log, structure file.log. So by applying these formulas, you can easily create your silicon nanowire junctionless FET. So this is the 3D structure of nanowire junctionless FET. This is the 2D structure of nanowire junctionless FET. And this is the simulative current that has come after the simulation of these nanowire junctionless FET. So for the same, I would like to thank you for listening to my video. I will update and come up with the next video of silicon nanotube junctionless FET. Thank you. Thanks for watching my video. Please stay tuned.